All right, so this one here, ML100. Let me get my Google Colab, which I like to use a different browser for because I've got it logged into some accounts that I like to use for this. I've got Opera. So let me close these other tabs and go to Colab. All right. All right, here's Google Colab. If you haven't used Google Colab, you can use any Python environment you want, but I highly recommend using Colab because it's fast and free, it's easily available to everyone, and it has the right versions of libraries and everything available. So I'll just make a new notebook. You log into any Google account, and you can run a Python environment in Colab. The only limitation is they only give you so much processing power, and if you try to run something that takes longer than about an hour and a half, it will hang up on you, saying we aren't trying to give you long-term things. You're only supposed to be doing prototypes, but you can do anything you want in here. So I can import TensorFlow. Let me put this on the left. There we go. So I can execute here, import TensorFlow, and it's nice and fast because it's running on Google servers. And it's connecting, and it's going to tell me, it tells me how much RAM and disk I have here. I've got 12 gigabytes of RAM and 100 gigabytes of SSD available, so it spins up sort of a virtual machine and lets me use it. And you can even get GPU time and such. So here it's imported the library, the TensorFlow library. And so here we're going to do, is it 100? Is what I wanted to do today. Let me make sure I've got it right. It was, in fact, 100 today. Okay, fine. So we're going to talk about 100. So we're going to talk about the basic concept of machine learning here. So we're going to do a linear relationship. And what's going to happen here is we have some data that we measured. I'm using fake data just to get the idea here. So we've measured x going from -1 to 4, and y goes from -3 up to 7. So I have some kind of y I've measured as a function of x. And in traditional science, the kind I used to do long ago, you would measure something and then a human would make a model. Like, well, it looks like there's a linear relationship. In fact, you can see here, after a human looks at it, a human will figure out y equals 2x minus 1 is what you've got here. And we're going to show how machines can make that decision. So we put in this code. I'll put in another block of code here. All right, so here's the data, x and y, -1, 0, 1, 2, and so on. And now we just make a machine learning model, and we fit. And what we're doing is we're learning with one neuron. This is the simplest kind of machine learning model. We have x go in, it goes to one neuron, and the neuron just does a linear calculation on x, mx plus c. And it's going to fit these two parameters, m and c, the slope and offset, for the best fit. So we fed into the model that we're going to try to put a straight line through the data, and the model is going to learn what straight line to put in. It's not going to be a human figuring that out. So this is the sense in which they call it machine learning or artificial intelligence. And the way it works, the typical technique is this stochastic gradient descent model, which is what you have here, SGD. It's going to use the mean squared error, what we talked about. It's going to take the y value predicted on the line compared to the right y value, square that, and add that up. So it's going to start with just random parameters. And then you can use this process of partial derivatives to figure out in any high order parameter space, if you make a small step, you assume that that will have a linear effect on the output, and you can predict what direction I should move to make the error go down. That's a simple predictable calculation, and you take a small step because it's probably curved in a large region of parameter space, but if you take a small step, you can reasonably assume that it's a straight line for a small deviation. And so the loss will go down. Here we are with the parameters. The loss is currently 2. It takes a step. The log goes down to 2.1, 1.8, 1.5. That's how stochastic gradient descent works. It's the general technique. It's like putting a ball down in a hill, and it rolls down the hill to the bottom. And as you see, the loss is going down, down, down. It's doing 500 steps, calculating the model 500 times. And you notice the loss finally gets down to 0.001. And now it's not really changing very fast at all, but eventually it gets extremely small, 10 to the minus 4, and I think it eventually gets down to 10 to the minus 5, and that's because our data is perfect. If you have y equals 2x minus 1, it will completely hit every point perfectly, and so the model gets pretty close. And so to test it, I predicted the value at an x of 10. And since the right fit is 2x minus 1, the correct predicted value is 19, and you see it got 18.98. So the model fit pretty well. Now I might want to see the x and y that it predicted. So I can add that here. I can calculate it, and then I can print out what's called the weights. The weights are the parameters that are being adjusted here. The weights are the slope and intercept of how the input is calculated in each neuron. So here it is doing 500 epochs. Now it's just got about 8 data points, so each calculation is very simple. So it doesn't take very long to do an epoch. You see it's only like 50 or 100 milliseconds per step. So 500 steps is just a couple of minutes. And see the loss is 0.01. Loss is getting down to 0.00. And I guess the loss should still get down to 10 to the minus 4 or 10 to the minus 5, because it should be possible, just like before, to fit it essentially perfectly. And when it's done, it's going to print out, here's the parameters, 1.99 and minus 0.99. The correct slope is 2, and the correct intercept is minus 1. And as you can see, it got within 1% of the right answer. So this is good. If you give it a very simple machine learning task, it's able to learn those parameters. So that's nice. Now, let's try adding errors to the data. I just put some random noise in the data to make it a little more realistic. So I go back to my data here, and I'm going to put that in. Now, I could just leave it like this to override the previous data, but I just feel better about commenting out that line. So now where I used to have 3, I have 3.1, and where I had 1, I got 0.95, and so on. I just added a little bit of noise to the data. So let's see how much that hurts it. Now, the loss is like 1. The loss is going down, down, down. So this is good. But before, the loss went down to 10 to the minus 5. And now the loss is never going to get down that small, because you can't draw a straight line perfectly through those points because there's errors in the points. So it looks like something like 0.01. Well, getting down to 0.008. Anyway, there's some limit to how low the loss can get. It's going to be a lot more than 10 to the minus 5 with that noisy data. I'm just trying to scroll my lines here so I can see the bottom. All right. It's jumping 10 at a time. There, it's done. So the loss got down to 0.004, which is a lot more than 10 to the minus 5. But again, it learned a slope of 1.99 and an intercept of minus 1.00. So again, it got within 1% of the right values, even drawing a line through noisy points. So that's reasonable. And so now you can try other things. Here's y is x squared minus 4x minus 5. So this is not really a straight line at all. But the model has a linear assumption built into it. So it is going to try to draw the best straight line it can through data that is not a line. And what will happen is it will just get a really terrible fit with a high loss. I'm not going to bother doing it live. It's actually going to be 4, which is ridiculous. And then we can do this one, which is more interesting. Suppose we have a complex curve, and we're going to take a more complex model. Instead of having one neuron, we're going to feed x into a neuron. It's going to calculate slope and intercept. Then it's going to feed that into a hidden layer of 3 more neurons, where they each get the output of this one, and another hidden layer where each neuron gets everything from the previous layer, and then combines it to one output layer. So we feed in one x value, and we get one y value, but the actual calculation in the middle is far more complicated. This is how it tends to work. All these parameters, there's going to be a lot more parameters in that model, and here's how you do it. You have a layer with 1 unit, then I'm going to have a hidden layer with 64 units, and another hidden layer with 64 units, and then one output layer. And so the result is that's going to have a whole lot more parameters to adjust than just 2, slope and intercept. Let's run this one. This one is more interesting. So I'm going to, I'll just make a new clean notebook. All right. And put in that stuff. All right, and somewhere, here's my data. To calculate data, I'm going to take x times cosine x plus noise, 0.1. So I'm doing, this is going to be a wavy curve, very far from a straight line. And I'm going to generate 1,000 points to trace out that data. I had 1,000 data points with noise tracing out a curve. Then I'm going to fit it with this model with 4 layers with 1 64, 64, and 1 neuron. So one thing it's going to do is show me the structure of the model, which will be interesting here. once it gets ready. Since I made a new notebook, it's going to spend about 30 seconds spinning up the virtual environment. All right, here we go. Now notice here I have, the first layer has one neuron with 2 parameters. The next one has 64 neurons for 128 parameters. The next one has another 64, but each one of them draws from the 64 before it, so that's another 4,000 parameters. So now the total number of parameters is 4,355 instead of 2. So you clearly have enough adjustable parameters to fit a very complex situation. And here it goes. The loss was 0.08, 0.8, 0.2. The loss is going down. It is learning, again with these stochastic gradient descent, taking little steps through that 4,000 dimensional space, adjusting all those 4,000 parameters from original random values down to values that lower the loss. And here's the result. The blue dots are the data points, and the red is the predicted model. So you see it looks like it fit pretty well, which is reasonable. 4,000 parameters are enough to fit it. But now you can play interesting games. You can say, for example, what happens if I only have one hidden layer of 64 instead of 2? How much does that mess up the model? Well, you can find out. The simplest thing now is we'll just remove one of these 64 layers by putting a comment in front of it. If I can get the mouse to move there, the pointer, there. So now I just have one 64 hidden layer, not 2, so it's going to be a much simpler model. And there it goes. So now instead of 4,300 parameters, I only have 195 parameters. And so it's a much simpler model. Now still, I would think 195 parameters ought to be enough to predict that data, but we're going to see. So there it is. The loss is going down, down, down. And if I can get, hey, there's the result. And as you can see, it's pretty terrible. It's doing a really crude approximation of tracing out that curve, much inferior to the previous one. And so there are various alternative models to try here. And here I have you try many different combinations and see which one is best. And then you can vary the number of input points, and you can vary the size of the noise to see what effect that has. So, you get to see how this linear approximation works, and that gets you started. So let me stop this recording.